now the next speaker is Sarah. So her talk will give practical skills for computing photoluminescence for the models with explicit spin polarization, with unpaired spins. We will, after her talk, we will go back to background and ramp up to this level of development in a little more continuous way. Okay, Sarah, floor is yours.
Thank you, Dr. Killian. Hello, everyone. So I'm going to briefly explain about how to generate the emission spectra for the spin polarized case. So as I talked, previous weeks, in order to run this Matlab code, we need some files, including the RRR file, bound out diff, bound out sum, energy pop, formaster, and absolutely the Matlab code. So as I mentioned previous week, we need to modify a bunch of numbers in the Matlab code. We need to specify the number of HOMO, LUMO, the range of orbital that we want, the number of steps, as well as the cell size in the z direction, and of course the transition that we are interested in. In this case, we kind of sorted the always the strengths file and we are interested in the transitions with the highest oscillator. So after modifying the Matlab code, if all process goes well with the Matlab code, we ended up to some plots. So one of them is, as you can see in the left, the energy dissipation as a function of time and as a function of space in the right panel. Also, we can see the relaxation rate for the electron and holes. So electron is kind of showed by the yellowish color, and the hole by the bluish or purplish color. So next and final images or pictures that Matlab plots for us are these three panels. As you can see from top left, this is the dissipation of excitation energy as a function of time, and also as well as on the top on the right, it is the emission spectra, and also time integrated emission in the below the time integrated emission. So you can see that each peak corresponds for a specific transition. So for my case, the highest intensity for the excitation energy corresponds to the LUMO to HOMO, and also we can modify this range of energy to our desired range of energy with just very simple. We need to just modify this part of the Matlab code, which the a-axis, it's a Matlab command that you will tell it that which range of x-axis and y-axis you are interested in. In this case, for the x minimum x, we want minus 3.03, and the maximum of the x axis as a 3 electron volt, and for the y-axis we wanted the range from starting from 0 to 7.3 electron volt. So I'm done. Thank you. Is there any question?
Please join me. Thank you, Sarah. So it was a record brief. Thank you. So any questions in the audience, online or in the chat line?
Which transition is below LUMO HOMO? Still there are some peaks.
Excuse me, Dr. King, can you repeat the question? I think Dr. Tapa is far away from microphone.
I still see some peaks below homo transition. What are those peaks?
You mean these peaks for this figure?
Below, yeah, that peak. Yes,
I'm not sure. We need to double check the O strength file and see which transition or correspond to this energy level. So I'm not sure for this case what are each peaks correspond to. I think just these two are kind of more important for us, which was LUMO to HOMO and this one LUMO plus 2 to HOMO.
Sorry,
So
I think what Dr. Safa, what Dinesh is asking, just generally, qualitatively, how to interpret presence of optical signal below HOMO-LUMO gap. Not literally which individual, but generally, what is it?
Something like, for example, maybe it corresponds to LUMO minus something to HOMO, or so.
So let me reformulate the question. Those transitions below the gap, do they happen from between valence and conduction band, from valence to valence, from conduction to conduction, or like which of the three options?
Still, I'm not sure about the answer for this question.
Anyone wants to try? We will have several talks to focus. So let's mark these open questions for all of us, and try to get it from each next speaker.
Can I ask why we think the LUMO plus 2 to HOMO transition is so much more important than them, when the one that like 0.8 EV is like 2 orders of magnitude higher intensity?
Okay, let's maybe, Sarah, please prepare to answer a question of David, and I will contribute a little bit to the question of Dinesh.
Okay.
So, and Sarah, would you please go to the editing mode so that one can put a little annotation? Editing, exit the presentation mode and go to the editing mode.
Let's see.
Yeah, thank you. The question that Dinesh did ask is showing a conflict between intuitive thinking and objective calculations. So there is a process that one can agree that we go from higher excited to lower excited by scrolling several orbitals in valence band and conduction band, and then at the end we come to the HOMO-LUMO gap. So the HOMO-LUMO transition between valence and conduction band seems to be to have the lowest transition energy, right?
Yep.
Yes, agree. But we were in this little exercise. We were thinking that the light can be emitted only to ground state from an excited state. But in addition, there are processes of radiative transition between several excited states. So if you go between individual electronic orbitals radiative way, then the transition energies of this little processes will be below the gap. Sarah, would you approve?
Yeah. Mm-hmm.
Okay, so this question is done. Now let's turn to the question by David.
So the question by David, why these two transitions are important. So the LUMO to HOMO is, as Dr. Klein said, I think we expected to have the lowest excitation energy and the highest intensity. So just we wanted to see that if we are right or wrong. So that LUMO to HOMO is for that. But LUMO plus 2 to HOMO. So for this one, actually, since we have for the in our paper we had a kind of a figure that has all 3 spin multiplicities on it. So this one is just for the n up down 1 or the low spin multiplicity. So on that figure that all 3 were together. So we just showed this transition. I think we wanted to comparison it with the maybe the other 2 spin multiplicities. So I think the reason was that because of the comparison, but I'm not sure that if any other reason is there is any other reason for this one or no.
David, are you satisfied with the answer? Sure. Okay, David is happy.